So here we have the last lesson of the year. And what we are doing here, something maybe a little bit more challenging. So we have this function, and it says find the value k that makes the function continuous. And obviously we have a piecewise function with a k in it in addition to an x. So what we want, right, I'm going to draw you two pictures. We have these functions that meet up at x equals -4. And what we want, right, is that our two pieces meet up. Okay, I don't know what the slope of that second one is, because that's k. So we want this. We want them to be continuous. Or the function, to be continuous. And what we do not want is something like this. So don't necessarily know what it would look like. But what we do not want is them to not line up, the two pieces to not line up. So we do not want, what am I trying to say? Do not want. Because they're discontinuous pieces. Okay? And that's at, again, x equals -4. Okay? So you may be seeing where this is going already, especially if you're here after watching the last lesson. What we want is for the two pieces to be equal at this particular x. So we want kx plus 20 to equal 2x plus 8 at x equals -4. Okay? I think writing this in your work is actually super helpful because it's sort of a different type of problem, right? We're taking two things and we're stating what we need to be true, and then we're going to figure out what number makes it true. Right? So it's a little bit different than just like, I'm solving this equation. So it's an interesting type of problem. This is actually some of the first like sort of calculus type reasoning you're doing here. All we're going to do, this at x equals -4 might be your cue here, is we're going to plug in -4 for each of my x's. So I'm going to get -4k plus 20 equals 2 times -4 plus 8. And then I'm just going to simplify. So -4k plus 20 is chilling. Here I get -8 plus 8, which is 0, right? And then from there I subtract 20 on both sides. And I just get k equals 5 when I divide that out. Okay? So that is my k that makes the function continuous at x equals 4. So I can even check if I want. X equals -4, I should have said, right? So my function then would become f of x equals 5x rather, plus 20, and then 2x plus 8. And then at x equals -4, what I get, right, is I get -20 plus 20 is 0. So this piece becomes 0. And then I get -8 plus 8, which is also 0. Okay, so those two pieces are equal, and that gives me the situation where my two line segments meet up. So what you're doing is you're setting the two pieces equal to each other, and then you're plugging in that boundary in this case. I want to show you just a couple of other cases here, just so you've seen them all. They're very similar. So this one actually looks exactly the same. So I want kx squared to equal kx plus 20 at x equals 2. And then this gives me 2 squared is 4k equals 2k plus 20. And I solve as I did before. So I'm not going to solve the whole thing. Just make sure you're plugging it into the x and not the k. But notice we have sort of a multi-step equation with k's on both sides, so that makes our math a little bit harder there. And then here's where you start needing to pay attention a little bit. So here, notice I have something really similar, but I have a quadratic equation, or rather I have a k squared. Okay, so what I want here is I want k squared plus 18x to equal kx at x equals -3. And then be careful where I plug it in here. So here my squared is going to stay because it's my k this time. plus 18 times negative 3, whatever that is, negative 54, plus negative 3k, or equals negative 3k. And this is now a quadratic equation. So let's remember what that looks like. So we get negative 54 here. And then we're going to add 3k on both sides. So I'm going to get k squared plus 3k minus 54 equals 0. And then I'd solve by factoring, right? So I get k, you guys are good at this. K, what do I get here? Plus 9, k minus 6 equals 0. So my two k's, we're going to have two answers here, would be k equals negative 9 and k equals 6. Okay, so that's a possibility. Remember, watch for, these are called quadratic equations. And you can solve by factoring. These you should be able to solve by factoring. You shouldn't need a quadratic formula or anything. So that's something to watch out for. And just take a second, make sure before moving on you know the difference. You notice the difference between the two. So it's the x squared on top versus the k squared is where we run into a quadratic equation because we're finding k. All right. So here what we have is something a little crazy, right? So I have this rational function on top. So we studied these first semester because it's made of a fraction, right? And then I have just plain old k on bottom. Okay. And then we want for x equals 4, right? So we find all values of k that would make the function continuous at x equals 4. So we don't care about anything else, but we need to know what's happening with this top function at x equals 4. So these work a little differently. You're not going to set them equal to each other and solve anymore. What I want to do instead is factor that top part. And notice no solution is also an answer choice. And factor the bottom part and see what I get. And let's see. So we have x squared. Oops, no, I want to say x plus 7. That's what I meant to say. And then x minus 2, right? What was what we would get when we factor the top. And then we have x plus 7 again. And then x equals, let's see, x minus 4. So there is our factored rational function. So this is my top part. So this is f of x for x not equal to 4. And we want to figure out whether we can make the function continuous. Okay, so we need to remind ourselves what happens here. So one set of factors cancels out because x plus 7 over x plus 7 is 1. And this is left over. Okay, so remember what this means is the function has a hole at x equals negative 7, the term that canceled out, and a vertical asymptote, where now we know it's called an infinite discontinuity, at x equals 4. Okay, so what this means, right, is if I drew this function, I'm just going to draw a random sketch, we might have something like this, where we have this going on at x equals 4. And then we also have a hole over here at x equals negative 7. Okay? So let's go back and think about what this is saying, right? So this is saying that this is the function everywhere except for at x equals 4. Okay? Well, if k was the function at x equals negative 7, we would have an easy time, right? Because we just solve for what that y value should be by plugging in negative 7 and make that our k. And then we kind of plug that hole, right? But we can't plug this hole because we have an infinite discontinuity. Okay, so if I make a dot, in other words, no matter where I put my dot in this asymptote, it's not going to make my pieces meet up. I still have to pick up my pencil to draw this function, right? So in this case, this is a no solution. So when that x value that it asks you about falls on a vertical asymptote, says submit the empty set. That's just a very pretentious way of saying no solution. You're going to say no solution here. There is no k that will make this continuous at this point. Again, we could do it for x equals -7, but not for x equals 4.